Let's talk about aromatic compounds. Continuing our journey from conjugated systems, we'll go ahead and now look at the most ideal conjugate system, that of benzene and similar compounds. Something special about benzene that we may have hinted on in our previous semester of organic chemistry is that it doesn't react the same way that normal alkenes do. For example, if we take cyclohexadiene and react it with excess bromine, we will end up brominating this molecule at all of the alkenes present. It's very easy to tell this in the lab because bromine is a very brown liquid, very dark, very obviously colored, and cyclohexadiene is colorless. And when we react them, we see the brown color going away very rapidly. This indicates that the bromine is reacting, and if we perform spectroscopic techniques upon our product, we will see indeed that it is brominated. However, if we try the same experiment with benzene also clear, no reaction takes place. We see the brown color staying around, indicating that bromine is present, meaning it's unreacted, and spectroscopy will reveal that the benzene is unchanged. So something special is happening here, because we're expecting, oh, well, we have more double bonds, that should be more reactive, right? However, experimentally, that's not the case. And further, if we try and take some similar compounds and hydrogenate them, we might be able to calculate the heats of hydrogenation, right? Just like we did to see that this conjugation of dienes provided extra stability, we're going to see the same thing happens with benzene. If we hydrogenate cyclohexene with one alkene, we get out about 120 kilojoules per mole. If we do the same thing with the cyclohexadiene, we're expecting around negative 240 kilojoules per mole. And in reality, it's a little bit less due to the conjugation, right? So it's actually about negative 232 kilojoules per mole. So it's a little bit less than we're expecting, right? And we've got that cis conformation as well. So we might expect this to be about negative 360 kilojoules per mole that we should get out in energy. But we actually see about negative 208 kilojoules per mole. It actually takes less energy to hydrogenate benzene than it does to hydrogenate, rather we lose that amount of energy. It's an exothermic process, right? We lose less energy by hydrogenating benzene, even though it has more double bonds than the cyclohexadiene does. And we might expect it, we saw that there's a small conjugation effect that lowers the energy of our cyclohexadiene just a little bit by 8 kilojoules per mole. For a linear alkene, it's about 15. But for the benzene, we see that benzene is 152 kilojoules per mole of energy less than expected. So there's an enormous amount of stability in here. Conjugation provided a stability of about 15 kilojoules per mole. But benzene, having the 3 conjugated double bonds within the ring, is 152 kilojoules of stabilization energy. And this energy is so special, it's so phenomenal, it's the reason benzene doesn't react like normal alkenes. We call this the energy of aromaticity. And the name aromaticity comes from the word aromatic, which means fragrant. And that comes from the fact that the original compounds that were looked at that were found to have this extra stability were ones that came from plants that had very strong fragrances. So very pleasant, strong fragrances like sandalwood. And as a result, the word aromatic came out. And just because chemists decided not to change anything about that, we still call it aromaticity. And so throughout this chapter, we're going to study the characteristics of what makes something aromatic. What does it mean to be aromatic? How do we name aromatic compounds? What are a few reactions of aromatic compounds? And then in the next chapter, we're going to really look at substituting aromatic compounds. And that's where the bulk of the reactions will come in this set of chapters here. And so in our next video, we'll talk about naming benzene and its derivatives. We'll look more at the structure of benzene. And then we'll start looking at the reasons benzene is aromatic, followed by looking at other compounds that are analogous to benzene and looking at whether those are aromatic or not as well.